Welcome to the Crypto Acceleration session. I hope you all guys enjoyed the banquet yesterday and you are not too tired. Our first speaker will present us A53 Make or Break, a massively parallel FPGA architecture for exhaustive key search. Konstantina, the floor is yours.
Thank you. Thank you very much, Victor, for the introduction. Wait, I changed from here and this. Okay, let's go with this. Good morning, everybody. Thank you very much for coming after that very beautiful banquet yesterday. I'm Konstantina Miteloudi. I'm currently finishing my PhD at Radboud University under the supervision of Professors Leila Batin and Nele Mentens, who, as you can see, are the co-authors of this work. The title is A53 Make or Break, a massively parallel FPGA architecture for exhaustive key search. And I'm going to show you why brute force attacks are still relevant and can still be interesting, at least for a hardware designer. So A53, you probably have not heard it before, is the basic algorithm that is being used in security of mobile communications, and specifically to 2G networks. It belongs to a big family of algorithms, the A5 family of algorithms, where A51 and A52 are already broken since they were using 64-bit key. But A53 is a stream cipher. Supposedly, it uses 124-bit key, but this 124-bit session key, it creates it by concatenating 64 bits. And it is based on Kasumi block cipher. Kasumi is the one that uses basically the 148-bit keys. So practically, this means that the effective key space for A53 is 2 to the power of 64, and that makes it a good candidate for exhaustive key search in today's hardware. In the same family of algorithms belongs A54, which uses 128-bit session key. Now you are going to wonder why 2G networks are still relevant, why someone would care about 2G networks, where they still exist. Even though they try to phase them out, there are some timetables. UK has set a deadline to phase out 2G and 3G by 2033. We expect that 2G will still stay with us as a legacy network for a long time. Either it's a fallback network, so when you don't have coverage from 4G, from 5G, your phone will go back to 2G, or it's being used in rural areas where no coverage exists at all, or it's being used in machine-to-machine communication between sensors and in emergency calls, for example, eCall and more. If we take as an example Malaysia, where we are right now, they phased out, they completely shut down 3G, but they have 2G alongside with 4G and 5G. And here is a map from GSMA website, where, as you can see, where we are here in Kuala Lumpur with very light. Can I point with that? Wait. No. Okay, I cannot point, but you can see that with light pink color is the area that has only 2G coverage. So you can see that they are still with us and they are still relevant. So we wondered, can we practically run an exhaustive key search for A53? What hardware can we use? Today's hardware, is today's hardware powerful enough to do something like that? How long it will take, and how much this hardware cost? So let's go back a little bit to other hardware devices that did exhaustive key search. The most common one is DeepCrack in 1998, where they broke DES. But this was a custom hardware design. These are ASICs, these are custom chips built in collaboration of government and governmental institution and companies. In order to build this custom, it was expensive and it needed specific, knowledge to do that. Then, a couple of years later, when FPGAs became more popular, became a little bigger, became more available, we have Copacabana. Again, it was a collaboration of academy and industry. Well, they built a cluster of 120 Spartan 3 FPGAs on one host. where they also did brute force attacks not only on DES, but other algorithms, and also other various cryptanalytic attacks. So, but all still here, we needed someone to build this hardware, and we need someone to know how to program this hardware. We still needed hardware designers with a lot of experience. And then we come to today, where FPGAs have become bigger, more dense, with more logic in them, and they can be everywhere. They are in the cloud. Everybody can have access to them. And not only that, but the vendors, specifically Xilinx AMD, has made the tools in a way, has made abstract tools like HLS, where everybody, not only the hardware designers, but also software designers, can go and program them. So, from a custom hardware that needed to be built by specific organizations, we have come to cloud, where everybody has access and everybody can program an FPGA, a big computing power. So, after we decided which hardware, which device we are going to use in order to run our exhaustive key search, we said, okay, let's examine how this works, how the communication works. So let's assume that this is our channel. On the left, you see the mobile phone. On the right, you see the cellular base station. A53 takes the 64-bit session key. It takes also a parameter called count, which is obtained from the frame number of the time division multiple access. What is this? If we have a channel with the same frequency and many users need to use it, we need to split it into time slots, and each time slot has the ID count. It produces 114-bit keystream, which is stored with a plaintext and produces ciphertext. And on the other side, we go to the base station, where it uses the count and the key session, and then it stores again the ciphertext to take the plaintext. And this is the procedure. So what do we see from here? We see, in order to find this 64-bit session key, we need to have a plaintext and a ciphertext, and we need to have the parameter count. I think at this point, I'm not sure if I have to remind how brute force attacks work. It's the simplest form of attack. It's the attack that all other attacks are being compared to. We have a plaintext and a ciphertext, and we systematically check all possible keys that, for that plaintext, we can take that specific ciphertext. So basically, you don't need to know spatial mathematics or spatial cryptanalytic properties. You have your cipher, and you need computing power. So looking at this, we were wondering, can we get the parameters, these parameters? I mean, we wanted our attack to be in the real world. So can we have the count, the plaintext, and the ciphertext, the count and the keystream in order to find the session key? Thankfully for us, at Crypto 2024, there was a work by Avoine et al., where they did extensive experiments in the lab with mobile phones and base stations, and they showed that indeed you can obtain a session, if you can capture a full session, and you can have those parameters. You can have the plaintext and the ciphertext and the count. So basically, if you have the plaintext and the ciphertext, you can have your keystream. So you can continue, we can continue from there. So what is the problem now? Our problem now became, how fast can we generate the keystream for all possible keys? At this point, I would like to point out that Kasumi and A53 are two different things, and if someone attacks Kasumi, doesn't mean that someone attacks also A53. But let's see a little bit about A53. It consists of 5 blocks of Kasumi, consecutive 5 blocks of Kasumi, executions of Kasumi, in order to produce 228 bits of keystream. At the beginning, we have an initialization vector where all the parameters are constants except for the value of count. And we have our session key, 64 bits, where we concatenate it to make it 128 bits. And we give it to the first block of Kasumi. We take the output, and then in order to produce the first 64 bits of our keystream, we again need to run another block of Kasumi. Looking at that, so we say, okay, we need to implement this. How are we going to implement this efficiently? These Kasumi executions cannot be parallelized. These need to be run consecutive. Okay, we said, we could just add pipeline registers. Still, adding pipeline register would help us with timing, but couldn't help us with resources. A basic key on a brute force attack is that you can run your algorithm in parallel, in many parallel cores, as many as you can. So this is very time consuming, so we cannot put it as it is. Then we thought the following. What if we took only the 64 bits, the first 64 bits of our key stream? What would we expect from that? We would definitely expect that we would have the right key stream, but we would also might have false positives. So on average, we have always one key, on average, one false positive. We said we can afford that. The examination of the key stream, if it's positive or false positive, we can do it later in the host CPU, not in the hardware that runs the attack. So we said, okay, this is our first optimization. We will not run the full A53, we will run a part of it. Then we start building Kasumi. Kasumi is a freestyle structure. It has 8 rounds. It consists of 2 functions, 2 basic functions, FL and FO, that are being between rounds interchanged. One round FL is first, the other round FO is first. It has 2 S boxes, 9 and 7 bits. It has a key schedule where from the 128 bits key you create for every round and for every function sub-keys. And it also has inside the FO function, you have also the small FI function. We can see that this is logic, this is XOR, this is shift, this is AND, this is basic, this is combinatorial logic. What you see with the red rectangles are the places that we decided to put our pipeline registers. When we decide to put pipeline registers, we want to balance the combinatorial logic between them. We want them to be even. This was a procedure that done repeatedly. We started, the first was to put pipeline register after each round. Then we saw where we had excess of logic, and we started adding pipeline register. And after every addition, we were running out of context synthesis. We had set up a goal that our core, our basic core of attack, wanted to have a clock of 500 megahertz. Practically, that means 2 nanoseconds. So that every time we added a pipeline register, we were running synthesis, we were checking if we have that clock, and then we continue. I mentioned synthesis because if at synthesis I can reach this clock, that means that my logic has that delay, and whatever logic I'm going to have later on in the process of implementing this will come from the placing and the routing of the design on the FPGA itself. It's not about how I put the logic in the FPGA. So we have this is our basic core of attack. We have the 2CAS module. It takes as input the count value, important, the known key stream that we need to compare, and also a start point and an end point. That's basically the keys that I'm going to examine. I have this core can examine the full key space, 2 to the power of 64, or subspaces, smaller subspaces. The key generator is practically a counter. We start from the starting point, we increment every cycle by 1, and we get until we reach the end point. We feed the key to the 2CAS module, we take the partial key stream, we check it with a known key stream. If we have a match, then that key is being written to the BRAM inside the FPGA, and then it's going out later for a further evaluation. And then at the end, we have a comparator where we say, okay, the key space that you want to examine is finished, you examined all the keys that you wanted, that's it. Okay, this is our basic core, and then we said, okay, we designed it, we like it is as it is, it's quite independent, it doesn't need to communicate with other cores. The communication with the outside world is very limited. Once it will take the start, the end point, the count, and the known key stream, that's it. It doesn't need to take any more inputs. It starts generating and checking keys, and at the end, you take your keys, your possible keys, and a value that says, okay, and that's it, you are done, you checked everything. Then we said, okay, what FPGA we are going to use? AMD has Alveo U250 FPGAs that are very commonly used in the cloud. You have data centers, you have servers where they have PCI Express, and they connect up to between 4 and 8 Alveo FPGAs. But Alveo are not hardware, let's call it hardware design friendly, because it has the logic, it's split, the logic elements of the FPGA are split between 4 regions for an equal region, SLR 0, 1, 2, and 3. And we have specific communication with the PCIe. We need to use AXI-bus, specifically, not something else. And we have communication also with the global memory and the host. So the first thing is, okay, I have my cores. First thing that someone thinks, I have my cores, I'm going to put them all inside, as many as I can inside the FPGA, I'm going to see what will happen. So here we have limit in the AXI bus that we could use in the FPGA. So we needed to pack our cores. The basic core that you saw in the previous figure should become a kernel. And the kernel should communicate with the rest of the FPGA. We already know that the SLRs don't need any communication between them, okay? And we said, okay, after extensive search, 4 cores for 1 kernel, and all the kernels are going into the SLRs. At this point, not only we had an increase in the resources because of the AXI-bus, we also had a delay in the communication. We also had some delay in the communication. So we said, okay, we are going to use 2 different clocks. Since we wanted from the beginning to have 500 megahertz in our basic computation core, and since Alveo offers that clock, we're going to keep it. And then we will set the communication between the AXI and the PCIe to 300 megahertz. We implemented our design, and as you can see, first we have Kasumi takes up very little resources, 0.28 of the LUTs and 0.08 from the flip-flops. Then we go to our own core, the core that you saw. That's a little bit higher, but we cannot have a linear scale to the 104 cores, again, because of the resources. We also faced another problem with Alveo. The numbers that they report that we have available are not the numbers that indeed we have available. We have no idea why AMD has done that. So that's why you see a utilization only of 69.14% in LUTs. We also have, in FPGAs, in general, in modern FPGAs, there is also an upper limit. You should use 80% of the utilization, otherwise the tool cannot place and map and route your design. So what do we have? In one Alveo, we managed to put 104 cores of our design. The clock frequency that we had was 496.7 megahertz. That means practically that approximately every 2 nanoseconds, we examine 51.72 billion keys per second. Another thing that we wanted for our design was to be scalable. The idea was not only to use it on Alveo, but we can use it even on smaller FPGAs, on heterogeneous systems, on heterogeneous FPGAs, and the only difference would be maybe the clock frequency. Maybe we could not reach, for example, the 500 megahertz, but still we can scale it. So at the bottom, you can see the number of cores that go into one FPGA. They communicate with the FPGA with AXI from level 0 to level 1. Okay? With color is what we implemented. The uncolored are what someone in general can implement in theory. Then at level 1 with the PCIe, we go to level 2, where we have our host. One host can have a specific number of FPGAs connected with it. And from there, we can go to the network where we have a super host, a super user, where what will it do? It will just divide the key space into key subspaces, depending on the number of cores that we have. It can give the parameters inside, starting point, ending point, and the count, and the known key stream, and it will expect the candidate keys for further evaluation. Now, execution time and expected time. In brute force attack, these two things are a little different. We have the execution time, what is practically, it's k, the number of possible keys. In our case, it's 2 to the power of 64. T is the time for one key evaluation, in our case 2.013 nanoseconds. And C, the number of cores, and B, the number of boards that we can use, divided by the number of cores times the number of boards. In our case, it's 104, and again, one board, one alveo we had. But we have also the expected time, because on average, we expect to recover the key in halfway of the full search. When we search the full space, halfway we expect to find the key. And this is execution time divided by 2. Then we wanted, since we wanted to do this to be practical and to be connected with the real world, we needed to check prices, except of time. We need to check also prices. How much this cost today? So as you can see, in the axis, in the x-axis, we have the number of FPGA boards, specifically U250, that can be used. On the left, you see the time in days, and on the right, you see the cost in millions. The unit price at the time of writing the paper was $8,311 US dollars. So, what can we say? We can say that with 8 FPGA boards, we can have, and the cost of $66,000, over 8 months, a little over than 8 months, we can enumerate the key space. If we go a little higher, with 256 FPGAs, we can do that in under 2 weeks, but with a cost of $2 million. So it's all a matter of how much money someone can have to give on that. So we created a brute force attack connected with the real world, where the whole key space, if we want to do it in 1 day, we can do it with a cost of 34 million, which I know that it might sound a little more, but we have heard recently in the news people spending that amount of money on different data centers. A53 should not be considered secure anymore, and I think it is known already that, but okay, we can show it more. Someone can go into the cloud and make this attack. Again, you don't need to build specialized hardware anymore to do a brute force attack. The specialized hardware is out there, is available to everybody. And for Microsoft Azure specifically, that cost per attack is $81,823. All legacy systems should be evaluated, specifically because they are in critical infrastructures, they are in sensors, they are in actuators. And we believe that our work can be used as a framework of accelerating more complicated cryptanalytic attacks. In order to do a brute force attack, you really need to consider many optimization at many levels. We did it at algorithmic level, we did it at design, and we did it at design level. And if you want to protect your own phone by yourselves, some Android phones have this. This is a screenshot from my own phone, where by default, they send you to 2G networks as a fallback, but you can go and check your options, and you cannot allow that. I mean, for emergency calls, still you can do calls, but if you are in a 2G coverage area, your phone will not be connected at all. Thank you.
Thank you, Konstantina. Any questions?
Hi, thank you for the very nice talk. I had a question about the number you had in your penultimate slide, which was the $80,000 for an attack. What did you mean exactly by the cost of an attack? Did you mean in the cloud? Did you mean like the whole key space, or? So
this is the unit price of one alveo. If we say that we want to buy it.
Yeah, I was talking about the number in the slide after, which is the cloud, the Azure one.
Yes.
Is it 80,000 for the whole key space?
Yes.
Okay. Thank you very much.
Thanks for the talk. Could this be extended to like multi-target, sort of multi-key attack, right? Like you're going over the whole key space, but also there's the count input and the like plain text input, so you'd have to. Wait, I guess not, right?
Wait, I'm not sure. Wait. I'm not sure. So are we? So yes, let's see the figure. This is what we are searching. We are searching for the session key, the KC. We need to know the count, and we need to know plain text and ciphertext. And there is a work at Crypto24 that showed that we can obtain this.
Yeah, I'm just saying, like, if you have multiples of these, right? Like,
Yes.
you measure multiple, you have multiple keys that you're targeting.
No, this we did it now for one key. Yes, but we can extend it for multiple keys. It's just what you will give inside your Cora, what count value you will give, and what non-key stream. That's it. If you want to give different, yes, you can make it completely for. So this approach, you can have it for half course, for example, to do this for this key stream, the other half for the other. Yes.
Okay, thanks.
I mean, if you see here, it's the superhost. Wait, it's the superhost that decides what to send inside. And we can decide to send whatever, yes.
Thank you for the presentation. Can you go to the slide number 12, please? 12.
That one, yes.
I'm curious why in the region 1 you have only 4 units, 4 kernels, while in the other regions you have 7 kernels.
They are not of the same size. They don't have the same number of loots and flip-flops. They are not equally divided, so each SLR is not equal to the other, unfortunately. We needed to experiment on this, how much we can fit.
And regarding the cost of the attack on the cloud, it is constant. So if I understand it well, because if you rent 2 units instead of 1, then you paid twice more, but you have it in half time, right?
Yes,
Okay,
yes,
okay.
yes. That's why it's constant. Yes.
Thank you.
Thank you.
Thank you so much. Excellent talk. I have 2 questions, if you don't mind. So the first one is, you said that 3G networks will be deprecated or already deprecated, but 2G will remain.
Yes.
Why do you think that is?
They are being used more. They are being used more. So instead of phasing out 3G, they prefer to phase out 3G first, and then they say, okay, let's keep 2G a little longer with us because it's a legacy. We cannot get rid of it as easily. It's already in too many devices, and we will see in the future what will happen. But yeah, the future comes very fast, faster than we expect.
Okay, thank you so much. The second one, you mentioned that you guys use 2 different clocks, correct?
Yes. One moment. Yes.
Do
So the cores operate at 500 megahertz. All the kernel operates at 500 megahertz, and whatever is outside that kernel operates at 300 megahertz.
Is there any disadvantages to having 2 clocks in the same system, or?
We needed more logic to add. This reduced the resources that we had because going from one clock area to the other clock area, we need cross-clocking domains. We need specific small circuits to do that so that we have valid data from one to the other when they pass from one frequency to the other frequency.
Okay, thank you so much.
Thank you.
We are running out of time for this talk, so sorry, I suggest we take the rest offline.
Thank you.
Thanks, Constantina.
Thank you very much.
Thanks, Constantina, again. Our next talk is POTA, a pipeline of Livius transfer acceleration architecture for secure multi-party computation. And Wei Jan will do the presentation. Please.
Okay, thank you. Thank you for having me here. Unfortunately, my PhD student, Xiaolin, who's the first author, has graduated and is not available. So I'm here on behalf of him. So today I'll talk about the OT accelerator for the MPC. And so first, it's about the background that we all know that MPC is, it doesn't require any trusted third party, and it can allow multi-parties to ensure that their input is secure, while they can each party can get the correct results. So MPC can be used in multi domains, for example, the medical, financial, and AI domains. So far, MPC is not widely used in the industry because it's poor performance. I think it's somewhere between the trusted execution environment and the full home-modified encryption. So that's something we need to solve. And according to the existing research, we can see that So for the local network, local area network scenarios, so compared to the plan test computation, the deep learning performance like degree like 10 to the third, and for GPU it's 10 to the fourth. For the wild area network scenarios, things goes even worse. So now we need to figure out like how we can accelerate it. So the key part is the oblivious transfer protocol. So what is OT? Basically, we have a model, could be hardware or software, but it's in the middle of two parties. And for the Alice, it's trying to like send two data, A0 and A1 to the OT, while the Bob will send one bit that could be either 1 or 0. So if it's 0, he will pick the OT will pick the A0 and send it to Bob. Otherwise, will pick the A1. So in that case, Alice like doesn't know like which message Bob actually choose because he can't get the R, right? And Bob won't get the other message. If he get like A0, he don't know what A1 is. Otherwise, he don't know what A0 is. So that's the key part of the MPC. And based on, I will try to like figure out like how important OT is in the MPC. So we actually run for like 4 benchmarks. These are like basic operations. For example, the multiplication, metric multiplication, bitwise and conversion operations. Also, we also test them with different network bandwidth settings, like the 5 gigabytes per second, 320, and 100 megabytes per second. So, as we can see from the result, that oblivious transfer protocols actually it takes like almost 90% of the MPC time, which means the OT protocol is the major communication overhead in MPC. So that's what we need to solve. Okay, from the previous slides, we talk about some basic OT protocols, but now we want to like look at some state-of-the-art OT protocols. So one is called IKMP, and the other one is called silent OT. From the first two figures, we can figure out that for the IKMP, it's actually pretty efficiency under the local area network, but it's pretty bad for the when the bandwidth goes lower. And for the OT, silent OT, actually it doesn't require the specific network bandwidth, so it performs pretty good for both LAN 1. And on the other side, we after this, so the previous one about communication, right? And for the later two figures, we are talking about GPU utilization, which is referred to the communication capability. So for the IKMP, it has pretty high demand under the LAN, but low under the N1. And for the silent OT, it has pretty high calculation demand for both. So that means for the IKMP, it is still it's related to the network bandwidth setting, but for the silent OT, it doesn't. So if we choose the silent OT, we can basically ignore the network, but we have to focus on the communication part. So that comes to the conclusion that the network, the bottleneck of the silent OT actually shift from the communication to the calculation. Okay, so let's focus on the silent OT. This is a framework. This of our other works. So we have 4 steps. For the first one is called setup. Basically, during the initialization part, we will generate some small seeds and send them to both the sender and the receivers. And for the second span and the third concatenate, we will start to generate more random numbers and try to extend to like a set of corresponding seeds. with the RPN assumptions. And later, for the fourth stage, we call transform, we will start to do the communication between two parties again by sharing part of the information. So this is how silent OT works. And as we said, for the communication cost, it goes lower because we only have very slight communication between the first stage and the last stage. So I also have very low complexity. It's all login. Also, for the communication, however, for the calculation part, it has a higher cost. We have to generate like millions of random numbers, and we also need to calculate some very large metric. So, for our contribution, I think to our knowledge, this is the first hardware accelerator that's supporting the silent OT, and it's not limited by the low bandwidth setting. For example, like in the cloud, like it's definitely the bandwidth is much slower than the local network. Also, we also designed some specific hardware modules to accelerate the different operations. For example, the random number generator and some large max vector multiplications under the RPN. And for the third one, we try to solve the performance issues between the host and the accelerators. We'll talk about later. So this is the overview of our POTA design. And basically, we have three parts. One host contains some application files, drivers to handle all the stuffs. And we also have two FPGAs, and both FPGAs are the same, has the same architecture. And in each FPGA, they have three parts. One is the SNS subsystem to do the communication between these two FPGAs. So we consider these two FPGAs as two parties. And for the DMA subsystem, it's basically used to communicate between the FPGA and the host via the PCIe. And for the compute engine, we have some specific stuff there that we have some random number generators modules. We have the LNP modules to the to generate the MOSIs, and we also have the Beaver triple to do some other jobs. So this is our architecture of POTA. So the first thing we want to propose is that we call it puncturable pseudorandom functions, PPRF, which is trying to generate the random number in a fast way. So basically, people use like some pseudo, like AES or hash to generate some pseudo-random number with secure requirements. But to our from what we have found that CHES may be a better solution because it has simpler algorithm with fewer rounds and also have like a very smaller hardware resource implementation. So what's more important is that CHES has like twice length of the self-test compared to the input, but for the AES, basically they have the same self-test and plain test also the key. So that's the advantage. Also, for the performance side, we try to do like a full pipeline architecture, which can like reduce the data dependency, which also like we also like reduce the data dependency per stage. And for the security consideration, we do some like research job, and also we run some tests to guarantee that CHES has the same security requirement like compared to the AES and the SM4. So this is our first contribution. And for the second part is that we try to find a way to accelerate the large metric vector multiplier and the RPN assumption. So the basic challenge is that usually this operation, if we write under like a CPU or FPGAs, it may require very high storage space. Also it requires like a very high memory bandwidth. So our solution is to use the EA code to like reduce the storage overhead and then meet the bandwidth requirements. We actually leverage the some feature of the metrics to minimize the hardware. So these are the details. We try to like decompose like a very large metric into two parts. One is called expansion metric, which has a random metric with some fixed row weight, and the other one is called like an accumulation metric, which has like ones on the like left corner, and we have all the zeros elsewhere. So these are the detailed design for this part, and we got the PPRF from the various slides, and we'll use the accumulator and expander to calculate the metrics. And for the third contribution is that we propose some host accelerator execution pipeline. Usually the latency between these two parts is pretty bad. I mean, they have very poor performance, and even we use the highest PCIe. So our solution is to use like design pipeline to like overlap the communication and the computation to increase increase the throughput. These are the detailed design that we have different like modules, for example, to generate random numbers, to do some calculation, and also for the driver and applications, we can pipeline after them. We can do this interleaving operation because we actually figure out that there's independency between the private data and functions, so we can do that. These are our third contribution, and now we came to the result section. For the OT protocol itself, so we actually compare them with some the two state-of-the-art OT protocol. One is called what we introduced before, the IKMP, and the other one is the silent OT. So as we can see, under different settings, POTA has better performance that could be as high as up to like 22 speed up. And these are for the comparison with software, and for the hardware solution, we also found some work that's based on the trusted hardware called HBCG, and we compare them with. We compare POTA with HPCD and the different network settings. Also, we compare with different modules for the OT and the oblivion line evaluator, and also the it's called associated beaver triple. And we can see that it performs better and can achieve like almost like 10 times speed up. And these are the performance of OT itself. Now we consider some applications for the MPC, right? So the first one is that we compare them with different benchmarks, as what we have seen in the previous slides, that we have multiplication, metric multiplication, bitwise and conversion operations. So from the red table, we can see that POTA achieves like up to nearly 200 speed up on the basic operations, and accelerate actually really can increase when the network bandwidth decreases. Also, for the last part, we use CNN as another applications. We can figure out that with different settings, POTA can achieve up to like nearly like 600 times on the CNN inference. And similar to the previous slides, that we also figure out that acceleration radio can increase when the network bandwidth decreases. So came to the conclusion part. We're trying to solve MPC performance issues, so we can use it, make it more practical for industry. And for our contribution, basically we're trying to merge the bottleneck from the communication part to the conclusion part, so we can easily accelerate them on some hardwares. So we post our POTA, which can accelerate them some performance up to like 600 times. Also, we have some other works like one is called MPC pad to accelerate the build triple that we also use this in our POTA architecture. Also, we have some future work collaborate with the CWI. So we will put three things together to like post a big picture of the MPC acceleration. And that's all my talk. And if you have a question, feel free to ask, or you can email to me. Thank you.
Thank you. Any questions? Okay, if not, I will start. Can you go to slide 13? I have a question.
Yeah.
Yeah. Can you give a brief description of what was in this HPCG and what's different from POTA, and if you could use some of your techniques in POTA to in this trusted hardware platform?
Okay, let me recall. So basically, the HPCG is used. It's a different kind of technology compared to the MPC, because MPC is part of the privacy preserving algorithms, but for the other one is use the trusted computing technology that it has very strong security assumptions that we have to trusted some of the hardware modules in the certain parties, so people can under these like assumptions, people can transfer data in a easier way, so the calculation degree could decreases. But for the MPC, is we had to guarantee the theoretically secure. So we have to follow all their protocols, which is much more complicated compared to the trusted hardware solutions. Yeah.
Yeah. Thanks. Any more questions? If not, let's thank the speaker again. Thank you. Our last talk of the session, it's accelerating hash-based polynomial commitment schemes with linear prover time. And we have two speakers, Florian Hirner and Florian Krieger. Please, the floor is yours.
So let's first check how it works. Perfect. So thanks for introducing us. So we will today present our talk about accelerating hash-based polynomial commitment schemes with linear times prover. It's a joint first offer work with Florian and me, Florian. So quite funny. Yeah, maybe let's iterate over the topic again and the motivation. So as in the invited talk on Tuesday, we already heard a bit about verifiable computing. So it's a bit different than in the case of FHE. So in FHE, you normally want to protect your computations. But in this case, you want to more outsource your computation, but you want to trust it. So you just want to make sure that the computations are done correctly, and you want to make sure that it's verifiable, that it's computed. For example, you have a machine learning model on the server, and you want to make sure that the correct machine learning model was chosen and executed. And so you want to really make sure that the integrity is there. And in case of, for example, you also want to introduce privacy, you can introduce zero knowledge proofs. So in this case, you don't need to reveal any data. For example, in the machine learning case, you don't want to reveal your weights. So in this case, you just use zero knowledge proofs. And in this case, you can also make sure that that is correct. So maybe let's go a bit more into detail. So to achieve all of this, for example, in the zero knowledge case, we need polynomial commitment schemes, and polynomial commitment schemes are central building block in proof systems. So what polynomial commitment schemes allow us is to prove a genuine evaluation of a polynomial. For in this case, it's f of x, and this f of x can be represent everything you want. It can be a machine learning model, it can be also different things. And in our case, we use the Orion linear time proofer polynomial commitment scheme. It's a three-phase commitment scheme. So we have a linear encoding, we have a leaf hashing, and we also have a Merkle tree. And these three functions cause substantial latency. As we already also heard on the invited talk on Tuesday, they take up around like 80 to 70% of the whole proof. Then maybe let's go a bit more into detail about these phases. So first, the graph-based linear encoding. In case of the graph-based linear encoding, we just take our polynomial f and just encode into a matrix C, as we can see on the left side. Then we just take each row of the matrix and encode it. So we get the encoded matrix C is then W, and then we take each row and encode it. It's quite simple. However, how is this done? So in our case, we just take the row and use a Spielman encoding. This is just an error correcting code. So we have a pipetted graph that maps the left part of the non-encoded matrix to the encoded matrix. And this part is then done on all of the rows after each other. And then in the next phase, we have phase 2 and phase 3. We will just combine them because they are quite similar. So we have the leaf hashing and the Merkle tree generation. In this case, we just take the output of the encoded matrix, take each row, and then commit to each row. So just take the whole row. It's quite large, so it's 16,000 bits in total, and we put into some hash function. You can put it into like SHA-3, Poseidon, or whatever. In our case, it's SHA-3, and then you get out a hash. And then you also do that for all of the other columns. And then at the end, when you get all of your leaf nodes, you just generate a Merkle tree. So you just take H00, H01, so these are neighboring nodes, and then it's quite commonly known that we just like recursively hash them together, such that you can have your tree-like structure. And this tree-like structure is really important for the verifiable part, so this is then used in the proof. So maybe let's also talk a bit about the hardware limiting factors here. So the commitment to proving is quite data heavy. All of the structures you saw here are quite large. So in case of 2 to the power of 16 and 2 to the power of 28 polynomials, they are multiple gigabytes large. So in case of 2 to the power of 28, it's 4 gigabytes just for the polynomial, and then 8 gigabytes just for the encoded matrix. So that's quite a problem when we think about hardware acceleration also. Then there is another thing, so the linear encoding is quite memory bounded, so it needs a lot of memory to generate these graphs, so we have to have a really fast memory to supply the data. And then in case of the Merkle hashing, we are quite resource bounded, since all of these units need to hash quite a lot of data. So in our case, it's like 16,000 bits, and hashing 16,000 bits needs multiple rounds of absorption, and these are quite hardware intensive in terms of resources. And we address all of these issues by introducing a new methodology for having a memory and platform hardware design. So maybe let's go one step up again, that we know where we are. So we normally have a host CPU, and then we also have a dedicated accelerator. Most of the current works, they propose an accelerator, an FPGA or an ASIC, and this ASIC or an FPGA has some HBM, so some high bandwidth memory connected to a hardware accelerator die. And normally what you're doing, you just generate your proof system and all of your circuit data, because it's quite randomly on your CPU, and then you just take the data, send it to the FPGA, and afterwards you have it in some memory, either HBM or DDR, and then you just stream it in your hardware accelerator. This is then done, and you just do some of your computations, and after the computations are finished, you just stream them back. However, this case now needs to be done multiple times, because you can't store the data on the chip. Since you have multiple gigabytes, and you need to stream the gigabytes of data into the chip multiple times, so that's quite costly. Then maybe let's go back to the platform part. In our case, we use quite a large FPGA. It was during the time the largest FPGA with HBM memory, so it has a peak bandwidth of 460 gigabytes, which is quite huge. However, to leverage all of this bandwidth, you have 32 pseudo channels, so it's not like DDR where you just have one channel and you need to saturate it. You really have 32 independent channels that need to be synchronized and saturated. Maybe to go a bit more into detail about the bandwidth, because it sounds really nice, however, achieving that is quite hard. And if we have a rule of thumb, so if you have linear read and write accesses, you maybe have a bandwidth of around 90 to 95 times, so it's still quite close to 460 gigabytes. However, if you're using frequent read turnarounds, for example, you do a read, a write, and a read and a write again, you already drop the frequency or like the bandwidth up from 460 to just 230. So it's quite a penalty. And then the most penalties if you do random reads, so just do random reads after another, then the bandwidth just drops by 30, down to 30%. So it's just 140 gigabytes of 460. And this is quite a problem. And most works don't address this. They just say, hey, it has 460 bytes. We just use it for our computations. However, if you're considering our case, we have the linear encoding. And this heavily relies on random accesses. And with this, I want to give the floor to Florian, because he will talk a bit more in detail about that.
Okay, thanks. Hi, also from my side. So we already learned about this linear encoding, and it has a lot of random memory accesses. So to reach a high-performance architecture, we now really need to think about how to reducing these random memory accesses. This is what I'm going to talk in the next slides. So the core operation of this linear encoding are expander graph evaluations. An expander graph is a bipartite graph which has a set of left nodes and a set of right nodes. And the left nodes in our case are just the message we want to encode, and the right nodes are essentially part of the code word. And each right node is just a weighted sum over some random subset of left nodes. And in their baseline implementation, the authors of Orion choose a left to right evaluation. So they are iterating linearly over the left nodes and distribute each left node to the connected right nodes. So to give an example, for example, in the first step, we just need to read L0 from the off-chip memory, and we need to store it in off-chip memory because, as already said, the data sizes are too large to keep in on-chip. So we read L0, we read R0, which is initialized to 0, but still it might already have some value at a later point. We perform a multiply and accumulation operation, and then we store the intermediate result of R0 back to the off-chip memory. Then we do the second connection from L0, which means we read R2, do the accumulation, and store R2 back. And this is repeated until we completed all evaluations of L0. And then we advance to L1 and repeat the same operations until we completed the whole graph structure. However, this approach has several drawbacks. First of all, we have really many read and write operations. And as you can already see, we need to interleave them. So there are really interleaved reads and writes, which leads to reconfigure the memory bus all the time, and which introduces a latency overhead. And we have pipeline hazard. So we have a read after write conflict, for example, indicated in this slide, where we must make sure to read the correct value of R0 from the off-chip memory before performing the operation in step 4. So this motivates us to propose a different approach, which we call inverted expander graphs, or in short, the right-to-left evaluation. So we have the same setting as before, but now we are iterating over the right nodes in a linear way. So how does this look like? We just take R0, initialize it to 0, and keep it on chip for now. And then we collect from the left side the right left node, or the correct left nodes, and perform the accumulation. Then we take the second left node connected to R0, do an accumulation, and so on. And only when R0 is entirely computed, we store it back to the off-chip memory. Then we go on to R1, do the same thing. In this case, R1 just has a fewer connections than L0. That's quite normal in the baseline operation of this graph structure. And we repeat this for the whole graph again. So as you probably already can see, it has different benefits. First of all, we need fewer write operations, and these write operations are now in a linear pattern, which is one of the big advantages. We have fewer turnarounds because these write operations can be bursted, and we don't have any pipeline hazards anymore, which makes the life of us hardware designer way easier. So to summarize, we really want to implement this right-to-left evaluation because it's just better for our setting. However, the problem is that these graphs are random constructions with a left-to-right setting, and now we need to turn them into a right-to-left setting. The reason for this is that each left node in the baseline case has a fixed degree, meaning the number of outgoing edges is fixed, and we cannot really generate this randomly on chip. So we need to come up with a different approaches. Our first solution for this is to just take the right-to-left graph and store it, or we generate it on the fly plus a post-processing. So the first one is more intuitive, the second one maybe a bit more involving, but we will have a look at on both of them. So to start with our stored graph approach, we first just take the baseline graph as it is generated in the baseline order scheme, which is in left node major order, which means that all left nodes are stored in one patch. And then we just reshape this graph and reorder the nodes such that it's stored in right node major order, meaning that all right nodes are in one patch, and we put this into off-chip memory. So this has a benefit. It gives the identical result as in the baseline implementation. However, as already mentioned, we again need more off-chip bandwidth. So we need to stream the data from the off-chip memory to the FPGA to perform the operations there, which is again a problem in our memory constrained environment. So what we proposed instead is to change the graph structure a bit. So we fix the right node degree now, that each right node has a fixed degree, which means that we can sample the whole graph randomly from a right to left approach. So this can efficiently be done using a small PRNG module on our chip. We don't need any off-chip graph memory, but we need to think about the security again. So we change the graph structure and we now need to show that this is still secure. So the situation now is that we fixed the right node degree and we collected some random left nodes, which we connect to it. So this leads to a binomial distribution of the degree of left nodes, and you can already see there is a red part of this chart, meaning that some left nodes have an insufficient degree such that the code has too less distance, which is important for reaching the soundness of the overall scheme. So what we do now is we introduce a post-processing where we just store these weak left nodes with the insufficient degree in a small on-chip memory. So this is feasible because this information is rather small, so we can keep it on-chip. And we introduce new connections from the left nodes, from the weak left nodes to some randomly chosen right nodes, which gives us this second chart here, so that each left node has a sufficient degree to reach the soundness of the scheme. And we also present a security argument for this in our paper, but I'm not going too much into detail now. I just want to present a theoretical analysis on how we can benefit from this approach in terms of off-chip transfers. So considering the left to right implementation, which is the baseline from the orange scheme, we can see that for a certain parameter set, we need 50 million read and write operations each for reading the data from off-chip memory and writing it back. Then we need additional 50 million read operations to obtain the graph structure from off-chip, which totals to 150 million data transfers overall. Now with our right to left approach, we can immediately see that we need way fewer write operations, which is a huge benefit, but still we need to read the graph structure from off-chip. And finally, with our post-processing approach, we can completely omit all the off-chip memory accesses to the graph structure. However, due to our post-processing approach, we need to have a few more reads and write operations, but the overall reduction is still significant, so we need only 2.6 times less off-chip data transfers, which is really beneficial for our memory constraint design. So with this theoretical analysis, I now want to hand back again to Florian. He's now going to talk about the hardware architecture and some actual results.
Okay, thanks. Now let's talk a bit about more of the hardware architecture. So we really prototyped all of this on an FPGA with HBM. So the setup looks like this, as in most of the chiplet papers also. So you have like an HBM connected via direct memory, and then you also have some DDRs for off-chip memory transfers, which are a bit slower. Then you have some super logic regions, which are called SLRs. So you have like region 0, region 1, region 2. And as mentioned in one other presentation, like they have different sizes. So in our case, they are quite similarly sized, and we have a custom shell such that we can use all of the resources here. Then in addition to this, we also have something called super logic lines. And in our prototype, this is quite important to know about, since to send data from one SLR to another SLR, you have to send them through the super logic lines, and they are only limited. For example, if you want to send data from HBM to the SLR1, you really have to route all of the bits to the next SLR, and if you want to send it to this other one SLR, you also have to send that, so you will limit your bandwidth between the chiplets. or between the superlogic regions. Maybe let's go a bit more into detail also. You also have to have a DMA structure. In case of like a normal VTIS flow, everything is done here, so you don't have to do it, but we had to build it with our custom shell. So you have to really have a data movement of 16,000 bits per cycle from the HBM and to the HBM, which is quite complex. But let's go more into detail now. So about the linear encoding part again. So in the linear encoding, as I already told, we have our C matrix on the left side, which is the message, and we have to encode it to W. What we're now doing is we just take all of these rows and encode them. However, all of these rows are independent, so we just can parallelize them and just encode them with linear encoding units. They are basically a bit more complex than MAC structures because you also have to do different accumulation parts. However, this part is more memory consumptive in terms of resource consumptive. And then again, we just packed it in an area and placed into the first SLR or SLR0. There is a reason why it's placed in SLR0, and that's really the bandwidth requirement. So this unit is the most bandwidth consumptuous, so it takes 32,000 bits per cycle as input, 16,000 as output, 16,000. And if you want to place another SLR, that's not possible because you cannot really route that data to another SLR. And if you route it to another SLR, you cannot use the other regions anymore. And then maybe let's also go to the next parts, to the hashing part. So we again have our W matrix, which is the encoded matrix. In this case, we just take all of these columns and hash them. However, all of these columns are 16,000 bits and we need to hash them. So we need around 16 absorption units. So we just need to have either one unit that runs 16 times or 16 unrolled units. In our case, we go for high speed, so 16 unrolled. But this is not really possible in reality. So we just were able to place 8 of them, and 8 of them really use 2 full SLRs. And what we're doing to achieve the 16 rounds, just we have a multipass design, so we just let the data rotate through this structure 2 times. And then we just pack them into 2 areas, and these 2 areas are then placed on the FPGA. So in our case, before we can place them, we also need to think about the data movements. And as I already said, we cannot move that much data, so we have a small on-chip scratchpad memory that allows us to reshape the data a bit to avoid sending all of the data from one SLR to the other. And then we just place the first hash array into the first SLR, the second one in the second SLR. And then we also perform our transfers from SLR to SLR to do the 2 passes. And then again, we also have a Merkle tree. We don't go into detail here. This is explained in the paper, but it's a simple feedback structure. And then at the end, we also prototyped everything and really ran it. So we have here our workstation on the left side and our chip on the right side. So you can see here everything is quite densely packed. So the first SLI has really a utilization rate of 98%. It was quite hard to achieve that and also to get it running then. And on the other side, on this SLR 2 and 3, we see this snake-like structure, and this is really caused by our SHA units, which are fully unrolled and feed the data really in a ring-like structure. And then at the end, after prototyping it and running it, we did some benchmarks. And in this case, depending on the polynomial size, we have a speed up for the commitment of around 264 times. The linear encoder has a similar speed up. However, the hash unit is quite fast there because it's quite data intensive and resource intensive. So we have a speed up of 1,015 times. This can also be scaled. So depending on the FPGA that you're using, you can either replace lesser units or more units, so the speed up will vary. And in case of the Merkle tree, we have a 21 times speed up. Then also for the proofing, we have a speed up of 64 times. However, in this part, it only takes a small share of the computation, and we just reuse all of the units that we already have, so the linear encoder and the Merkle tree, in just a different configuration. And in the end, we just want to conclude. So we really are the first hardware accelerator for polynomial commitment schemes, especially the linear encoder, the linear proofer time polynomial commitment schemes, Orion. And we present our new methodology for inverted expander graphs, and in addition to a proof to make sure that we still achieve the soundness that is needed in the system. And we also reduce the off-chip bandwidth by quite a lot to achieve these speedups. So with this, I want to sum up everything. We also have a small demo, but yeah, we couldn't do it here because the internet is really slow. So if you're interested, we have it on our laptops and we can show it then. Yeah, so thanks a lot.
Thank you. Any questions?
Hi, thanks for nice talk. Had a question. When you have a linear encoding matrix, can you go back to a slide? So yeah, here for example.
Yeah.
So each row has the same linear encoding?
Yeah, each row is the same linear encoding. So in this case, the first row, so row 0, will then be encoded, and this one uses the same graph structure as all of them.
So yeah, so each row will have in each output row you use the same input, the same links, connections. So why don't you? Maybe you did it, but why don't you simply transpose the matrix C and do the same computation but in buckets of 128? So instead of reading one C00, so instead of reading
yeah. Okay, I get it now. So like the main problem here is that like you only have 32 channels, and if you like transpose the data, you don't, like in our case, like 4 rows are in one channel, and we just feed it in this structure. However, if you transpose it, you cannot really store the data anymore because the rows are too small, and then you have to like really have a different logic to compute them. So in this, like in our case, like it's more efficient because like you can just use the bandwidth a bit more efficient in this case and parallelize everything. So it's also a different approach that could also work probably.
Okay, thank you.
I also have a question. So I think it's in this same slide, your hash chain.
Yeah.
And so how does the hash chain look like when you unroll the system? Do you pipeline it, or it's fully Ketchup unrolled? And what's the frequency you can run the system at?
So okay, in this case, like this unit here, like these units are like SHA-free units, and like they're really fully unrolled and fully pipelined. So we have 2 different configurations depending on the frequency we want to achieve. So like in terms of 200 megahertz, you have like 1 buffer per 2 rounds, no, per 2 states. However, like if you want to go for a higher frequency, like 400 or 300 megahertz, you really have to have a buffer between each stage. And this is why the unit is so large. So in our case, we just run it at 200 megahertz because it matched the HBM frequency.
Okay.
However, later you could possibly, but that's like a hard engineering task then.
Yeah. Okay. Okay, if there are no more questions, let's thank the speakers again. Thank you.